gets smaller because of the motion of the source, that makes the frequency get higher. And so if the source is moving towards the observer is going to hear something apparently different than the actual vibrating frequency of the wave. It's, like I said, a little different than the observer moving into the source, now that the source is moving into the observer, but the net result is a higher frequency. So whether the observer moves towards the source, or what I'm trying to show you now, the source move to the observer, there's going to be a higher frequency. Now, it's a higher frequency for a different reason. And your author kind of stops here with the math, and Physics 123 will carry this math a little bit further, and so we will see that the way you calculate it is a little different. But for this class, let's just get conceptually that there's going to be a higher frequency. Again, I think this animation does this one a lot better, so let me come back over to this animation and show you that what would happen here is if the source was moving, and so now I think you see it, the source is getting behind the wave, and it's crunching them together. And so right here, when they finally get to the ear, watch what happens. Boom, 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 at a faster rate. And so as the source is moving towards the ear, higher frequency. But now watch this. Now the source is moving away from the ear. And see how the waves going towards the ear are now spread out with a longer wavelength. The wavelength gets bigger. And because the wavelength gets bigger, now the frequency goes down. And so, again, it doesn't matter whether the source is moving away from the observer or the observer is moving away from the source. Either way, the frequency is going to go down. Now, it's for a different reason, but nonetheless, it still goes down. I think the best way to kind of explain this is if you've ever listened to cars, or even take a 5-year-old who loves to play with cars. They'll do something like this. You'll say, "Is that a race car? Does your car go fast?" They'll go, "Yeah." "Can you show me a fast car?" They'll go, "Yeah." "Well, let me see it." So they'll take the little race car and they'll go, "Did you hear that sound?" Right? The high frequency as it was coming towards you. And then the low frequency as it went away. Right? They know that there's a shift in the frequency. They know that sound. They've experienced the car coming towards them. High frequency. The car going away from them. Lower frequency. That's this Doppler effect that I'm trying to point out. And of course, I can't really make you move, you being the observer, towards me. I can't even do that in a face-to-face setting, so it has nothing to do with the remote learning here. But what I can do is make the source move if I do something like this. Oh, I can try to swing my microphone. Is that what you mean? Oh, hang on. Okay. Ron was just a suggestion. I'm going to try something first here, and then we'll try his suggestion here. But if I take this, I hope you can hear this obnoxious sound. It's 1,375 hertz right now. And if I hold this away from me, but so my microphone's not at the center and it's moving, I'll put my hand out. You hopefully will hear, and I guess I should stop talking, a shift in the frequency. And listen when I spin it slowly, I don't hit myself in the head, versus quickly. Right? There's a much bigger shift. And so that's referred to as the Doppler effect. Well, one more thing and call it quits here. There's just some really fun things, but we better move on. The Doppler shift, or the Doppler effect, leads in to shock waves, because the next natural question after moving forward is this. Let me turn on the display here. What would happen if you were moving faster than the source. And so let me just springboard to here. See how the source is moving and crunching the waves together, but it's moving slower than the waves themselves. What if this actually went faster than the wave? And what will happen is we will get a shock wave. It's what I would call an extreme Doppler effect is what a shock wave is. It's kind of neat to see here, and so this animation, I think, shows it best. Here is kind of our little animation of something going slower than the speed of sound. That's why we call it subsonic. And so here's this plane kind of pushing its nose through it. See how they're kind of crunched together here and spread out here. So as this plane, went by, you would hear this. Okay, this is still high frequency on this side and low. Watch this. This is what the plane picks up speed. And so now notice it makes the wave, but it moves faster than the wave it makes. So this is now going supersonic. But now you're beginning to see a pattern of superpositioning, if I can use that word from chapter 15, that begins to form here. Watch the next step here. Oh. Well, it's too slow. Okay. This is exactly at the speed of sound, which is called Mach 1. See how it makes a wave and then makes another one right on top of itself and another one right on top of itself and another one right on top of itself? It's the superposition. And so what you get is this ginormous wave that builds up. And so you don't get this continuous sound like a sound. You just get a food. It's a wall. Now, if you go faster than it, you don't get a wall in front of the plane. That's good. That's why it's so dangerous for a plane to go actually the speed of sound. But do you see how it's making a superposition in kind of a wedge shape? And so planes should never fly at the speed of sound because they make their own wall. But once they go faster than the speed of sound, so this is Mach 2, their superpositioning makes a V shape. And so if I was drawing a picture here on the board, any airplane, any bullet, any crack of the whip, any object going faster than the speed of sound then would look, well, so if here's the airplane, would make this high pressure wave. It's not really a sound wave because it's not like a frequency. You don't hear of a whole continuum of sounds like, no, you just have boom. It's just all added together. All of that is the superpositioning of all of those waves. And so somebody standing on the ground as the plane flies by, this shock wave will eventually get to them. Now the airplane will be kind of past them since they're going faster than the speed of sound. But they're just standing there. They can see the plane at first. They don't even hear anything. And they see it go past them. And instead of hearing the rumble of the airplane, they just hear this boom. And it's just this giant shock. And so it's why we call it a shock wave. It is actually just the superpositioning of all the sound waves added together. And so that's our shock wave. Now, let me point out a common misconception. This airplane always makes the shock wave. For some reason, there is a misconception that says planes only make a shock wave as they break the sound barrier. Not true. That's not when they make them. That's when they first make it. They always make it. And so flying across at a speed greater than the speed of sound, they are always making this shock wave. You, of course, only hear it one time because the wave comes down and hits you once. And then, of course, later on it hits somebody else. And later on it hits somebody else. A good example of this is water waves. The speed of water waves are so slow that most of the time, unless a boat's going really slow, and so you have what they call the no-wake zones in harbors and stuff. But most of the time, a boat is going faster than the speed of water waves. And because of that, they make a shock wave. You would call it a wake on a boat. And so this V shape behind a boat is a wake. And the boat always makes a wake. As long as the boat is going faster than the speed of the water waves, and the boat goes through the ocean, and so I can stand out here on the pier and watch these boats come out of the harbor all the time, and as soon as they give it throttle, as soon as they come out, they're going slow, they're not making a wake, then they go fast, and then they start making a wake, and I watch them come out, and they go out and maybe out to the oil platforms, or maybe they're going out fishing, or maybe it's a dive boat. They start taking off, they will make a wake the whole way. Now, again, somebody on the seashore is only going to get that wave one time. And as it maybe goes up the coast, then somebody further up the coast gets it. And further up the coast. And further up. And they only get it one time. So they may think, oh, that boat only made a wake one time. And that, no, it's not true. It was always making it. That's why, of course, it is not allowed for airplanes to fly supersonic across the United States. I mean, could you imagine a flight from LA to New York? I mean, it would make the shock wave the whole distance, and every single person under the airplane from LA to New York would get this shock wave. It would bug the heck out of their ears, if not break their windows. And so we purposely do not fly supersonic because of that. In fact, the only passenger plane that ever went supersonic was the old Concorde. And then it was restricted to only going supersonic when it was over the ocean, which was kind of its downfall because, you know, that was a good flight then from, say, London to New York. But then you got to transfer a plane, and then you have to go slowly from New York back to LA. And so it was just, you know, you don't want to fly it supersonic. Of course, now that doesn't mean we're not looking for other things. In fact, years ago when I worked for Boeing, that was kind of the thing we were looking for, the SST, the Supersonic Transport. You know, what could we do? And we tried some fun things, some different things. One thing that was a big hindrance to going supersonic is now you burn so much fuel. But working with NASA, it was kind of interesting. We put like these little paddles. I don't know how to explain it other than, can you imagine a boat going through the water, and then it had these arms that extended out with surfboards on the end, and it would ride its own wake. And so it would make a wake, but then it would use that wake to push it. And if the surfboards were enough to get the energy, they would then siphon that energy back off. And so it was a good experiment. It didn't go very far because then these things would make more wakes, and it just, there was always a shock wave. And the whole idea was to kind of try to eliminate the shock wave. If you couldn't eliminate it, the idea was we'll generate it and then we will absorb it and use that energy to push the airplane. And those were fun experiments, but nothing really came out of them. The latest approach is just to get out of the atmosphere. And so they're talking about, you know, LA to Tokyo in an hour. Oh, that's amazing. But it's not in the atmosphere. So you leave LA, go straight up out of the atmosphere, fly outside of the atmosphere, supersonic, and essentially re-enter. And then now you have the problem of space flight. How do you re-enter? How do you not burn up your plane? The parts are so damaged, can you use them again? Right now the answer is no, with some exceptions. That's the whole success of SpaceX, that they can actually reuse them. So a whole fun discussion here, but I better call it quits because I'm talking, again, way too much. Like I said, fun and neat stuff here. And why don't I say, let's begin the next chapter. But we're getting close to our hour and a half, and it probably doesn't make any sense for me just to take a couple of minutes here. So why don't I call it quit for our first lecture? I'll take a 20-minute break, swap out some of our equipment, and move on into the next lecture, and we'll get started with our other waves, the non-mechanical waves of optics. All right, see you in 20.